So today what we will do is we will have Jarrah come up and explain some of the radiation readings that were on the Polaris Dawn missions. The article that he wrote for ALICE was called Polaris Dawn Report, the Apollo Investigation by Jarrah White, or it's Apollo Investigation, Polaris Dawn Report by Jarrah White. Polaris Dawn did not prove that astronauts can survive the radiation on a flight to the moon. So, would you like to take it away, Jarrah?
Certainly. I have to say that I have been kind of distressed by some of the things that have been said in the media about the Polaris Dawn mission. There was obviously the media, they looked at the altitudes and they saw, oh, well, this is going to cross the inner Van Allen belt, and obviously they tended to jump on it and blow things out of proportion. And so something similar had happened previously with the Gemini-11 mission, and I felt it was time to step in and set the record straight. The Gemini-11, they started off with a circular orbit, a very low altitude circular orbit. Then they fired the Agena rocket to boost it into a more elliptical orbit, which allowed it to kiss the innermost edge of the inner Van Allen belt. Now, the belts, as I say in the article, the belts don't just suddenly stop and start as if you've just fallen off the edge of a pool and straight into the deep end. They start off shallow, proportionally. They start off very shallow, then they get more and more intense as you get closer to the heart of the belt. The Gemini-11 and also Polaris Dawn, they didn't get anywhere near the heart of the belt. All they did, as I said, they just kissed the innermost edge of the belt and then they dropped back down again. Gemini-11 did 2 of these highly elliptical orbits and Polaris Dawn did 6 of them. After that, they simply fired the rockets again and descended back to a more circular orbit.
Yeah, well, one thing that was interesting about this was about the radiation belt. Now, when Polaris Dawn was being put out there to the public, one thing that I did notice is that in the advertisements that they were running, they always showed the astronaut actually out there on a tether doing an actual spacewalk away from the capsule. But we don't see that. And another thing they said too was that they were actually going to enter into the very first radiation belt, which they never did, not walking in space. So I just wanted to throw that in there.
Yeah, well, like I said, all they really did was they just kissed the innermost edge of the belt. They didn't go much very far into that. That's been the whole Gemini-11 thing and the whole Polaris Dawn thing. They've both been blown out of proportion by people like Jay Windley and Phil Plait. Plait actually was in a debate with Joe Rogan, and I mentioned this in the article. He went so far as to claim, quote, the Gemini missions went deep into the heart of them and stayed there to make sure these guys could be in it. Well, that's false, because if they went into the heart of the belt, that would be suicidal. I have an actual graph from Kovalev, and he states very clearly that at the inclination that the Gemini missions used, the dose rates there are about 390 rem per day. That's at the heart of the inner belt. If you're going to be there for several days, that's going to be suicidal. Even a brief exposure at those kinds of readings is going to be suicidal.
Yeah, so just for the people that don't really understand this, can you just go over some of these values? Because some people don't really know what an MEV is. Like, for example, in Table 1, can you just explain briefly what MEV is?
Yeah, this graph here is purely for the 200 mega-electron-volt protons. A mega-electron-volt is the unit of energy. And so let me recall off the top of my head, 1 mega-electron-volt is about 1.6 by 10 to the minus 13 joules. Okay, so basically we use that to determine each of these particles carries that much energy, okay, and we use that to determine, okay, so many particles have impacted the human body, they've deposited this much energy into the system, and so to calculate how much radiation a person has been receiving, there's absorbed radiation doses and then there's equivalent radiation doses. The absorbed dose is basically the amount of energy deposited in the body. Okay, we usually use grays, which is the amount of joules divided by the mass of the subject. You can convert those to rads. And then what you want to do is you want to then convert to the equivalent dose, which we do that by basically taking the absorbed dose and multiplying that by a radiation weight factor. For protons, it's 5, and for electrons and X-rays and gamma rays, it's 1. And so for photons and electrons, the absorbed dose is the same as the equivalent dose. But in the case of protons and the heavier particles, there tends to be much higher than the absorbed dose. And so what Kovalev showed in his table here is that for 200 MeV protons in the heart of the Van Allen belt, you're getting several hundreds of rem per day. Okay, and so this contradicted Plait's claim that, oh, they were able to stay in the heart of the belt for so long. Well, first of all, they didn't get anywhere close to the heart of the belt, and you can see that had they done so, it would have been suicidal. Again, it must be emphasized, all Gemini-11 and also Polaris Dawn did was simply make some highly elliptical orbits, basically changed from a circular orbit, made to a high elliptical orbit, which basically took it within reach of the innermost soft boundary of the inner belt. And then they simply dropped down to the lower altitude again. You asked something about the spacewalking as well. This isn't mentioned in my article, but if you look at the actual videos of the, quote, spacewalk, it turns out to be more of a stand-up EVA because the guy had trouble getting out of the cabin. I believe we mentioned this on a previous show, but when I first saw the pictures, the unveiling of the spacesuits that they were using on the Polaris Dawn mission, I have to say, I thought, are they showing the right picture? Because they didn't look that much different from the pressure suits they usually wear during the launch and re-entry procedure of the mission. No. It looks like they just simply attached an umbilical cord to the launch and entry suit and just called it a day. By the looks of things, you can see he has trouble to move his arm. He can't really grab onto anything, and so he looks like he has significant restrictions in the suit, which might have limited his ability to get out of the spacecraft.
It is strange that these guys would be using those kind of spacesuits. One thing I don't understand, and we keep going back to this, so I don't want to harp on it, but the gaskets that sealed the faceplate to that helmet, the suit's all one. It's one piece that they put on, including the helmet. The whole thing is one piece. The one that I saw, because the fellow that was putting it on in the International Space Station, it was all one piece. And then they just clipped the visor down. But it's just the gasket around the visor. I just can't see how a spacesuit that almost looks like spandex can do anything.
Normally what you have, you see, you would have a spacesuit you would wear just simply to maintain suit pressure when you're basically in the ascent phase or the re-entry phase of the mission. And then if you were going to do EVA, you would have a dedicated spacesuit for that purpose, which has relatively more mobility than the entry suit and the launch suit. But for whatever reason, as I said, it looks like they just simply used the same spacesuit and called it a day as far as functionality is concerned, and it seemed to be an afterthought. There's a YouTube channel called Common Sense Skeptic who has done some critiques on the Starship and a few of other Elon Musk's undertakings. During his unveiling of the Rogan, he doesn't seem to pronounce robo properly, but there was a particular shot in that unveiling in which he's accompanied by a guy in the spacesuit. Common Sense Skeptic noted that the guy couldn't even move his head because of the limited mobility in the suit. That there seems like a big design flaw. Even on the shuttle suits and the Apollo suits, they have a much, much larger helmet. So even though it's fixed in place, you can easily look at this way and that to see where you're going, see where you can turn this and that, you know. So Musk seems to have this idea of making everything, let's just make it all look cool and futuristic, and whether it's functional seems to be an afterthought.
And another thing, too, that people were also saying about, well, why didn't they just take a camera out there and take some pictures and video? Well, they had a video camera in the helmet itself, so I guess they really didn't need that. But then again, they also didn't need any cooling tubes or heating tubes underneath the suits because they were hooked up to that umbilical. And I would imagine that the heat and whatever environment is required, plus the oxygen, would be in that tube.
I'd have to look into the specifications, but I believe they would have had some air conditioning tubing into the suit via that umbilical line. Usually what they have on the shuttle, and they started this on the Apollo missions, they would have these spandex suits with the water tubing, which would run through the suit to basically relieve them of the body heat. On Apollo, it was supposed to be vented outside the suit. When they were done with it, would then freeze to ice. And in the case of the shuttle, I believe they recirculated back into the suit. I also heard something about the modern shuttle suits being built like a thermos bottle to minimize the amount of solar heat to get inside the suit. But anyways, getting back to the article I wrote, we also discussed the South Atlantic Anomaly region in the belt, which of course is a region where the radiation dips much lower than usual. And this is one thing that the propagandists also particularly like to obsess about. They say, you claim the astronauts, they can't go to the moon because of the radiation belts. Well, what about the shuttle crews? What about the ISS? They all go through the South Atlantic Anomaly region. Well, here's the thing, right? The South Atlantic Anomaly region, first of all, the dose rates there are much lower than, say, the heart of the radiation belt. This was actually reported by Gautam Badwa, who was the radiation health officer at NASA. He's dead now, but he stated that if you go through the anomaly, the South Atlantic Anomaly, for 20 minutes, and for the remaining 70 minutes outside the anomaly, your body has time to do some recovery to the radiation. Now, Mary Bennett, she cited this in a previous Solus article she published back in 2002. When the propaganda saw that, it was obviously damaging to the false equivalence they were trying to push. Windley, he went so far as to deny that the astronauts have this healing ability. He says 30 minutes, not 20, as Badwa said. He says that sums up to 8 hours per day. The human body doesn't have a chance to do that kind of recovery in hours. He said it takes several hours or days for the human body to do some repair to this kind of radiation damage. Well, Here's how you know that that's wrong, because we have actual measurements aboard the ISS and also the Mir station, right? It shows the South Atlantic anomaly delivers something like 0.6 rad per hour. And so if you expose by 8 hours a day, that ends up being something like 4.96 rad per day. And so you can do the math for how long the shuttle crews and how long the ISS crews have been up there. That ends up being several hundreds or even several thousands of rem in the long run. Well, obviously, no shuttle astronaut has ever received that kind of dose. So obviously, their bodies are doing some recovery to the radiation inflicted upon them, whilst they're outside the anomaly. So Jay Windley, he was just lying here on his website. He tended to embellish the whole story about Gemini, not just Gemini 11, also Gemini 10. He said, oh, Gemini 10 went into the main belt itself. Not just Gemini 11, but also Gemini 10 goes into the radiation belt. Well, Michael Collins himself actually disputed this in his book, in Carrying the Fire. He says that they only went as high as the South Atlantic anomaly, and I've shown various statements by him in that book. He says, this region, known as the South Atlantic Anomaly, is where the radiation belt dips down, and at 475 miles will we be grazing at the bottom of it. Notice he says we're just grazing the bottom of the South Atlantic Anomaly. He's not saying we're going into the heart of the belt, we're not going into the deep portion. He's specifically talking about the anomaly. And so if you want to get some ballpark numbers, on Gemini 11, it was reported that while they were skimming the innermost edge of the belt, they reported something in the order of about 0.2 or 0.3 rads. And so looking at the transcripts, we find that they're only in there for about 30 minutes grazing the innermost edge of the belt.
How many rads would kill a person so that we can have an idea in our minds what is going on with these other ones?
It generally comes down to the exposure time. A dose of up to 500 rem is considered to be lethal to astronauts, and so any radiation dose measured in several hundreds of rem is considered to be life-threatening. If you receive something like 200 rems over a lifetime, you'll probably end up with cancer. If you receive it in just then, you're probably likely to die very quickly soon after that.
Okay, then this is what I'd like you to do, and then we can go back into the article again, because I really love this one. Can you tell us, when you were in school, when you guys were doing the experiment with the radiation, with the paper and using aluminum, how when you got to the aluminums? I don't want to spoil it, but that was crazy. Could you just give us a breakdown of what happened?
Yes, when I was doing my astrophysics course, I'll never forget this. This was my first year in physics. Okay, we were given some copper discs, which contained different radiation samples, different radioactive sources. One was an alpha emitter, one was a beta emitter, an electron emitter for all intents and purposes, and one was a gamma ray emitter. And we had a Geiger counter. The idea was we would put the different discs in the path of the detector, okay, and then we would measure the counts per seconds, okay, and then they gave us little different pieces of material to use as shielding. We had a little paper piece, we'd have a aluminium piece and a lead piece. Okay, the idea was we'd see how many of those we would need to reduce the counts to zero, or close enough to zero as possible. Okay, you've seen many textbook diagrams where they show the alpha particles, the beta particles, and the gamma particles impacting different pieces of material. They'll show, okay, the paper will stop the alpha particles, the aluminium will stop the beta particles, and the lead will stop the gamma radiation. Obviously, what we did first, we needed some control. We basically put the alpha emitter, we put the beta emitter, and we put the gamma emitter in the path of the detector with no shielding. Here's what it looks like unshielded. We ended up having something like 1,000 or 2,000 counts per second for the alpha particles. So then we put the paper piece in there. The count rate dropped to about 2 or 3 counts per second. Okay, that was expected. This was a huge shock to me. We put the aluminium piece in there, in the path of the alpha particles. Intuitively, you would think, okay, if the paper stops the alpha particles, then surely the aluminium will do a much better job of stopping them. Lo and behold, when we put the aluminium piece in the path of the alpha emitter, the count rate was actually greater than the unshielded count. What was happening there? Well, it turns out as the alpha particle hits the aluminium, it ends up getting fragmented, because you see an alpha particle is 2 neutrons and 2 protons joined together. It's essentially a helium nuclei. As soon as it hits the aluminium, it just fragmented, and the detector was essentially receiving the secondary radiation, this breaking radiation, as the particle gets stripped into pieces and then thrown in at the detector. It went straight through the aluminium, was fragmented, and that was what we were just picking up. So we actually had a higher radiation level than we had with the unshielded.
But then back to the Apollo program, that's going to cook those guys in the capsule, isn't it? Because it's aluminum, the aluminium craft. And that goes for the space station that they tend to put up around the moon. So I don't know about that. But anyways, I digress.
So Point is, yeah, normally what you would want to have, right, you would want to have a low Z material to stop the primary radiation. Then underneath that, you would have a high Z material like lead or something to absorb the secondary radiation. You'd have to put multiple layers of the aluminium or one layer of the aluminium and a layer of lead underneath there to stop the secondary particles from getting into the detector. That was our first-hand experience that we had in this physics class. The Polaris Dawn and the Gemini-11, we have the actual data from the mission. I actually was tuned into one of their live streams for a Polaris Dawn. Here's another thing that's quite interesting too, you see. If you actually look at the live stream and also look at the actual transcripts from Gemini-11, you find that when they did those highly elliptical orbits, they took place over Australia. This is significant because just much the same way we call the region where it dips the South Atlantic anomaly because, well, it happens over the South Atlantic. That's where the radiation dips to its lowest point. When it comes to the opposite side, the exact opposite is true. We have the much less radiation above my home country of Australia. Yay, Aussies, and so they specifically chose this particular orbit such that the highly elliptical thing would actually take place over Australia, where the radiation is at its lowest peak.
We're talking about aluminium at this particular time. Is not a Hasselblad camera made of that material?
They had a steel case, Scott.
Yeah, steel case, yeah. And
you sure not parts of it are made of aluminum?
Oh, the inner parts were. The parts where they mount. Because I have the whole thing.
Anything hitting that is going to excite the particles more and affect the film. The particles are going to fly apart and just be all over that film like crazy. And the cases, those ones that look like suitcases that they stored the box in to return the lunar rocks, those are aluminum. So what's radiating off the rocks, because they're irradiated, even though NASA says they're not, they're now inside the craft. Are they not going to magnify and enhance that radiation that they brought inside the craft as well?
That's an excellent point. Scott.
And they're sitting right beside it.
Marcus, you sent me an article a few years back about IMAX doing their film on their space station in which they had to use bags of water to protect the film canisters on their way back.
That's right, yeah. It was an interview with, I think, the producer of the IMAX film. It was about the construction of the ISS. They had 2 weeks. They sent the cameras up in the space shuttle. Then they filmed it as per the directions. Then they had to put the camera with the magazines still on board encased in the water containers. So it was protecting because they were fully aware that there were going to be problems from radiation. And this was the ISS. This is below the Van Allen belts. But they were protecting what they had available. And it was, 2 weeks they had to keep them up there before the shuttle came back down again. It was either the director or the producer of that film.
I remember I actually have a copy of that film on DVD, and I found that quite interesting that they had to go to those lengths to protect it from the radiation that's below the main belt. The only real significant radiation they had to worry about was the South Atlantic anomaly, and all the other radiation they would get would come in the form of cosmic rays, the cosmic rays that managed to get through the magnetic field and whatnot. The magnetic field really protects us from much of the solar and cosmic radiation, and the atmosphere protects us from the rest of it. In space, you get a little higher elevation from what you would expect on the ground, and many International Space Station astronauts have received cataracts as a result of that, exposure.
Something you mentioned a bit earlier about Joe Rogan interviewing Phil Plait. Do you know when that was?
That was in a debate they had on Penn Gillette's radio show back in, I believe it was 2005.
Okay. Yeah.
Yes, this was a couple of years, I think, after the Penn and Teller did that despicable program with Plait and Rene. And so, from what I understand, is they interviewed Rene for something like 3 hours. He obviously made the radiation part of his talk, and they cut and edited all of the footage and made it look like he was some drunkard. They had him drinking out of a vodka bottle, and he explained that he had his own water purification system, and he would use those bottles, whatever he had on his hand, vodka bottles, milk bottles, whatever, he would use those to keep that water he purified in. As he said, they were shooting them and they weren't supposed to be shooting.
That was done some years ago, that interview.
The TV show that he did was in 2003, and the radio debate with Plait and Rogan was in 2005.
That makes sense. Thanks.
Yes. As I was saying, basically the Polaris Dawn and the Gemini-11, they both made their highly elliptical orbits over Australia, where the radiation is the lowest, which obviously is a good opportunity for them. And Polaris Dawn actually had something better going for it because it had a much higher orbital inclination. The higher your orbit is inclined to the equator, the less the radiation will be. It thins out towards the poles. And so the Polaris Dawn, they had the inclination of around 50 degrees, which is comparable to the space shuttle. In fact, I've actually got the numbers written down here, as a matter of fact, towards the end of the article here. It was 51.7 degree inclination, the same as the ISS. On the Gemini missions and also Apollo, there was more inclined to the equator by 30 degrees. That's significant as well, because if you actually look at the numbers like what's been attributed to Apollo 11 for its outbound trajectory, you'll notice that the orbit inclination, it never exceeds 31.16 degrees. Now, this is significant. I've got a textbook by Wright et al. 2005. They say the particle density is greatest at the equator and low latitudes, then decreases as the latitudes increase. This is for the inner belt. They say at latitude 50 or 60 degrees north or south, the density of the belt is very low. In writing about the outer belt, this is the electron belt, they say, like the proton flux, the electron flux is highest near the equator and becomes negligible at a latitude of 60 degrees north or south. Well, it becomes negligible at 50 degrees. Obviously, Apollo has a problem there because their altitude never got higher than 31.16 degrees, which demonstrates, for all intents and purposes, they should be right in the heart, in the most intense regions of the belts. I actually have the numbers that were actually attributed to the coordinates. I got the coordinates for the Apollo 11 mission. This was actually published by Robert Brannig. There's a whole story about that. Like Clayton Windley, he had his own pro-NASA Apollo hoax debunk website. After I was done with him, he deleted any mention of the Apollo hoax from his website, and you can probably get why. What he tried to do was he found the coordinates that are attributed to Apollo 11, the coordinates in terms of magnetic shell and magnetic field strength, B over B naught. What you can use is you can take those L and B over B naught values, you can plug those into the industry standard model for the radiation belts. That's called the AP8. AP8 is for the protons, AE8 is for the electrons. I could only really use the proton model because for the electrons, they don't have a model for any of the electrons that would actually penetrate the Apollo spacecraft. Their model stops at 7 mega electron volts, and so you need about 14 mega electron volts for the electrons to pass through the spacecraft. With protons, it's easier. We need about 8 mega electron volts to go through the spacecraft. First of all, let me tell you what Brannig did. He took these coordinates, plugged them into the AP8, and basically got the fluxes for each interval of radiation. And so then he said, the spacecraft, it'll stop all electrons up to 100 mega electron volts, and anything greater than 100 will go straight through the astronauts and won't do much damage. What? That's incorrect. To make this claim, he was citing data from this old report. I actually found his references. Okay, his reference was based on a graph from 1935, 34, something like that. Basically, when particle accelerators were in their infancy, back when we had very limited knowledge on what will shield and what won't shield. And as far as anything greater than 100 mega electron volts going through the astronauts, that's just wrong. For a direct comparison, in proton therapy, that's where we accelerate the protons to a certain level. So we're firing them through this pencil beam at the tumor. Okay, the idea with protons is that if you accelerate them to a certain energy, they only travel so far and they tend to just lose all their energy at the maximum depth they can reach. They call it the Bragg peak. So you accelerate it such that the Bragg peak will be only as deep as the tumor. And then it releases all the energy there, it will kill off the tumor. That works fine for proton therapy, but in the case of the Van Allen belts, it's not a pencil beam. The entire body is being irradiated by these particles. It's all over the place. It's omnidirectional. The protons that we use in proton therapy are in the order of 200 mega electron volts. 200, 250, something like that. So that should give you an idea, right? And he's claiming that anything greater than 100 will go straight through the body. If that was the case, we wouldn't be using protons with energies up to 200 mega electron volts to penetrate a tumor.
Yeah, I was looking at this demonstration here, whereas the proton therapy, it stays inside the body. It doesn't go back out the other side, so it doesn't exit.
Exactly. So anyways, what I did then was I took Brannig's coordinates, found all the proton fluxes that I needed, and then I did the calculations to determine what would have happened. In fact, I actually showed the coordinates in one of my articles in column number 6 and also column number 5. Column number 5, that was for the proton fluences, which is where we're dealing with the total amount of particles from a solar flare. In the case of Article 6, I actually take the proton fluxes, this is in protons per square centimeter per second, and then I convert that into the rad per hour. Okay, so basically what you want to do is you get the proton fluxes, and this will be stated in terms of protons per square centimeter per second. Then I want to convert that to protons per square meter per hour. Okay, I got that. Then I want to multiply that by the surface area of a human, which is about 2 square meters. That cancels the area, and it gives me the number of protons per hour. This is the number of protons that have struck the human body every hour. Then I simply take the energy of the proton, multiply it by the flux I've got. That gives me the amount of energy per hour in mega electron volts. Then I simply convert that to joules. Then I divide that by the body mass of the human, and that'll give me the number of grays per hour. And you can convert that to rads. That's optional. I prefer to do that because it makes it easier to convert it to rem. Okay, so once I have my rem per hour, in the case of the Van Allen passage, we're basically just focusing on each minute of transit. If you look at the actual table, you'll see this is the time after translunar injection. So the graph shows that for the first minute of transit, that's when they first enter the belts, and it keeps going like that for the remaining 20 or so minutes. And so basically, I take that hourly dose rate, I divide that by 60, each dose for each minute of transit. Once I had my totals, your radiation ended up being something like 6.65 rads. Now, that has to be multiplied by the radiation weight factor of 5. This is something that I learned whilst I was researching this. I learned that for this particular orbit inclination, the AP8, even though it's the industry standard model, it actually has the tendency to underpredict the fluxes, because you see the AP8 is essentially just averages of satellite measurements made over the late 60s and the early 70s. This doesn't really take into consideration things like ejection events, like when there's a massive solar flare that can over-replenish the belts or create a third belt or this or that. The measurements have shown that for a 30-degree inclination orbit, the AP8 tends to underpredict the fluxes by a factor of 3. Okay, that's no problem. So I just take my doses and I multiply them by 3 to make the correction. So as you can see in the table here, for all the protons that would penetrate the astronaut's body and deposit their energy in the body, we find that the uncorrected dose would be about 33 rem, and the corrected dose would be about 99.7 rem. The reason I have two doses listed here is one is the skin dose and one is the body dose. The skin tends to receive the most brutal damage, you see, because obviously it's the one receiving the initial brunt of the radiation. It's sort of like a sunburn, you see. Just to put this into perspective, a skin dose of a few hundred rad is about enough to cause serious sunburn, and a skin dose of 2,000 rem is enough to require skin grafts. And so you can see from the numbers how severe the skin burns and the body doses would have been. So about 100 rem, that's life-threatening, as I said. In the skin doses, well, you think that would have been reported. They would go back, we had to rush the astronauts to the hospital because of severe skin burn surgery. Obviously, that never happened.
Yeah, but what gets me on Apollo is that they show such low radiation doses. Like, for example, here, you're looking at Gemini-11 here, I believe it is. Collins said that it was nothing more than a chest X-ray. Oh, I guess that's nothing more than a chest X-ray.
Yeah, well, again, the context matters because they're just talking about the innermost edge of the belt on Gemini, the South Atlantic anomaly. Okay, for the most part, it's the South Atlantic anomaly. Only Gemini-11 had the high elliptical orbit that would take it within reach of the soft boundary, the soft innermost boundary, whereas on Apollo, they're supposed to have gone all the way through there. And in the case of Apollo 14 in particular, Apollo 14 has the highest skin dose reported. Again, I say skin dose, not the body dose. NASA only reported the skin doses because its orbit took it much closer to the heart of the belt. And that right there is an impossibility. I got this particular book here. This is Astronautical Engineering and Science. There's a section in here, Problems in Radiation Shielding of Space Vehicles by J. Warren Keller and his group of scientists from the Marshall Space Flight Center. They basically reported that the heart of the belt, you would need something like 100 grams per square centimeter of shielding just to bring the doses down to 1 Roentgen. The resulting shield thickness are seen to be quite formidable, with approximately 100 grams per square centimeter needed to reduce the total dose rate to approximately 1 Roentgen per hour. We use Roentgens typically for measuring X-ray and gamma ray exposure. 1 Roentgen is equivalent to about 0.87 rads. Okay, so you needed that about a meter of shielding. If the material is water, 100 grams per square centimeter of shielding would be about a meter of shielding.
Now, we're going back to the Van Allen belts because this is interesting what you said here about the planet. So the Van Allen belts are not constant about the planet being denser in some regions than others. High apogee orbits for Gemini-11 were therefore planned to take place over Australia because the level there is comparatively low. Now Conrad reported to Carnarvon, our dosimeter reads 0.3 rads per hour up here. Gordon amended this saying Houston radiation is revised to 0.2 rads per hour, to which Bean replies, sounds like it's safer up here than a chest X-ray. So how many rads did you convert that to?
You'd have to multiply that by 5 to convert that into rems. As I said, you would need something like 100 grams per square centimeter of shielding to bring the dose rates in the heart of the belt down to 0.87 rads.
But he's saying 0.3 rads per hour. That's nothing.
Yeah, like I said, this is just the innermost edge of the belt. He's not going into the heart of it. This is just for Gemini-11, where he's just skimming the innermost edge of the belt. You see, like if you have a diagram of the belt in a textbook, right, you can imagine, okay, Apollo would have to basically cut clean through that, whereas Gemini 11 just skim around the innermost edge of it.
Okay, then let's go right into the heart of the Van Allen belts then. How many rads per hour are you going to get? For example, here these guys are going through there. Now they get right in the heart of the Van Allen belts. Let's just say they get right into the third belt. Like right in there, where the worst part of it's going to be.
Yeah.
Well, how many rads is that going to be per hour? What about gamma rays? Are they receiving gamma rays at that point?
The radiation in the belts primarily is protons. Okay, you will get gamma rays in the event of breaking radiation because, like in the case of X-rays, X-rays are generated when electrons are stopped in material. They tend to lose their energy in the form of X-rays. With protons, when they collide with other particles, they tend to release energy in the form of gamma rays.
Yeah,
Okay,
the gamma rays are what we're interested in because that's what's going to cook them, right? The gamma rays are going to be basically being reflected all around inside of that craft.
That's why you tend to need a layer of high Z material underneath the primary shield to absorb the secondaries.
Well, we haven't seen that in any of the PDFs now, have we? So there you go. There you go.